Okay, so for the second one is called graph partitioning. So this is a different, we have a different goal for this one. So for example, here we say a good partition satisfies two different two conditions. First of all, each part, when you get a partition of a graph, we want that each part is of a similar size. Okay, so you partition this in half, or like it's a bipartition. And then also we wanted to minimize communication between the two parts. So when you say like you have a bunch of nodes here, you have a bunch of nodes here, and then there are some nodes that's connecting here, and there are also some nodes like this. So here you can see that if I partition the nodes like this, then there are, like, for each part is 5 nodes. So I satisfy with the first situation. And the second situation is that like the edges that I cut are these 2 edges, right? So I only cut 2 edges, which is not bad, right? And also you can consider some other ways to partition this. Maybe, for example, I have another partition. So I used to have this edge. So let's say if we randomly partitioned these 5, 1, 2, 3, 4, 5. Okay, so these 5 nodes and this 5 nodes are partitioned into 2 parts. So each part also have 5 nodes, but in this case, I cut off 1, 2, 3, 4, 5, 6 edges, which is not good compared to the 2 edges that I cut. So there is, I think there should be a finite way to partition the nodes, but there is a minimal one, right? So there is one particular way to partition the 2 nodes that minimize the communications between the 2 parts. And that is the one that we wanted to solve. And with that said, right, so we are going to define the edge cut, which is the communications, basically what is the connections between the 2 parts. And we're going to call it edge cut EC of P. So P means the partition. And definitely we don't have to always say that we partition things in 2. We can say we partitioned K parts, right? So each V1 through Vk has a similar size of vertices. And then the edges that's between all of these partitions are being minimized. So the objectives, we wanted to make sure that each part has equal size, so load balancing, and we want to minimize that. Okay. So the mathematical model of this is actually a little bit complicated. So I'm gonna just skip the math part and let you know that there is a way. When you, I think when you take linear algebra numerical methods, you may have a better idea how to solve for this. But so far, we are looking at a minimization problem of minimizing the edge cut subject to the 2 parts being similar. And it ends up being solving a quotient, relay quotient of x. So x is a vector here you put in is of Rn, n is the number of nodes here. And then you're basically finding the minimum of the relay quotient of this quantity, x transpose times L times x, which is our Laplace form, divided by x transpose times x, subjected to the x being a normalized, right? So this means it's a normalized vector, and x transpose times 1 equals to 0. It means that there is equal parts of positive and negative, right? So these two are to some people's surprise, like these two are actually equivalent. Not exactly equivalent, but it's an approximate way of finding this the partition. And so with this we can solve for it. And for example, the one that I did was I inputted this graph. It's a 6-node graph that you saw before. And I found this one vector, which is actually the vector that's corresponding to the second smallest eigenvalue. I call it x2. So this vector is the x that minimize the Rayleigh quotient of x, minimize this quantity, subjected to the norm of it being 1 and the x transpose times 1, meaning the sum of all of this is 0. So you see that there are equal parts of positive and positive and negative values here. And the positive ones corresponds to the third, fourth, and the sixth item. And that means is the V3, V4, and V6. And the first one, second one, and the fifth one, they are negative. So that corresponds to V1, V2, and V5. And this gives you a natural cut, a separations between the two sets of nodes. So it means that these three should be in the one partition and these three should be one partition. And these two edges are the ones that we wanted to cut. Okay. So, and you can imagine that how do you get three different partitions? You just keep doing it, right? So it's a recursive process. You take one side and then you keep cutting it, and you take this side and cut it. But in this case, we have 6 nodes in total. I think 3 and 3 is probably the smallest, and then like you can't get any smaller than that. So this is also another applications that relates to graph Laplacian, right? So you also have this form here, but you're just solving a different problems. You get a different results. And with that said, I'm going to mention a few applications, very important applications of partitioning. So what we heard a lot in nowadays is parallel computing. Basically, what it means is that like if you have a very powerful computer that can calculate, for example, like 10 tasks at the same time, that basically means that for each task, is running on a different unit, like a different part in the computer, okay? So if you can parallel these things, then of course, less time is gonna take you for getting an answer. But in some cases, if you say like you don't partition the graph, and the graph has like 10,000 nodes, then everything is in a serial mode, like you're gonna calculate one by one. You don't get an answer before you get the answer for the previous nodes. Then it's very complicated. It takes very long to compute the whole thing. But if you can partition it, right, into different parts, and for each part is relatively the same batch, then you can send it to different part of the computer or like different GPUs, different cores, and then have each unit compute a certain task. And then in the end, you're going to divide the whole computation time by 10 or 20. Okay, so parallel computing is a very popular trend. It's a very popular topic right now, and it uses graph partitioning. If you're working on a very big graph, like 10,000 nodes or 100,000 nodes, it's very, very significant in terms of the saving in time. Spectral clustering. So this is also a very important idea in machine learning. So basically what it says is that you are going to look at the spectrum of the graph. So for example, you take a graph and take a look at its neighbor and cluster the nodes that have similar traits or similar characteristics. It may not be direct distance, or it might be some other properties. And then you can also group them so that you can define some properties of each node. So for example, you don't know these nodes functionalities before, but then like if you group those into different clusters, then if within the cluster, you know the nodes functionality, then you can deduce, you can inference for other nodes what does these nodes do. So this is, I think, is useful if you're dealing with, say, protein interaction networks or like social networks. It's very popular idea. And network analysis, this is very general. So network analysis, of course, when your network gets very complicated, and sometimes you have a lot of meanings on your edges, different weights, different directions, and the nodes also have different meanings. Of course, it's useful that you look at the graphs in a smaller spectrum, like you zoom into different parts, and without losing a lot of informations, meaning that the interconnections, the communications between each part is very minimized. So you didn't lose much by cutting these into different batches and just focus on the batch. So so graph partitioning, that is another applications. And in my research, I did both actually. So for the first one, the interpolations and the graph partitioning, both of them are in my research domain. So what I did is basically graph mining and network analysis. So I did different analysis on data sets. That's the user recommendation ones, the rating ones, social networks, protein networks. Those are very huge data sets. And of course, to do partitioning, to save time on those is very, very important.